Hey everyone, and welcome. So, what if I told you that most of those hard, dynamic programming problems you dread in coding interviews are really just the same 10 patterns, just wearing different disguises? Well, that's exactly what we're going to do today. We're going to demystify DP and give you a practical toolkit you can actually use.
Okay, let's just dive right in by talking about something I think we've all felt, that feeling of hitting the dynamic programming wall.
You know the feeling. It seems like this huge, intimidating barrier standing between you and that job offer. So let's ask the question that's on everyone's mind. Why? Why does DP feel so ridiculously hard?
Well, I'm going to let you in on a little secret. It has nothing to do with being a genius. It's not some magic you're either born with or you're not. Getting good at DP is all about one thing: learning to recognize patterns. Once you see the underlying structure, these seemingly impossible problems just start to click. So, what's the magic sauce here? What are these patterns actually built on? Let's pull back the curtain, because it really all boils down to two simple but super powerful ingredients. First up is this idea of optimal substructure. All this really means is that to solve a big, complicated problem optimally, you first have to solve the smaller, bite-sized pieces of it optimally. If you get the little steps right, you can combine them to get the big solution right. Simple as that. And here's where the DP magic really happens: overlapping subproblems. You see, if you just wrote a plain old recursive solution, you'd end up solving the same exact subproblems over and over and over again. It's incredibly inefficient. DP is smart. It calculates each little piece just once, saves the answer in a lookup table, and never calculates it again. And those two ingredients give us this beautiful universal three-step recipe. First, you define your state. Basically, what info do I need to solve one small piece of the puzzle? Second, you find the recurrence. That's the formula that connects the small answers to the bigger ones. And third, you just solve them in the right order, usually bottom up, building your way to the final answer. All right, with that foundation in place, let's dive into our first family of patterns. These are all about situations where you have to make choices or pick items from a set while dealing with some kind of limitation. And we have to start with the absolute classic, the OG of DP patterns, the knapsack problem. The core idea is always this: you're trying to maximize your total value, but you're constrained by some limited capacity, like weight. Now, I love this visual metaphor because it makes it so clear. Just picture a shelf, and it has a very strict weight limit. For every single item you encounter, you face a simple choice. You either take it and put it on the shelf, if it fits, of course, or you skip it and move on. That's it. Your job is to figure out the combination that gives you the most valuable shelf possible. Okay, and this leads us to a super important distinction you'll see in interviews. There's 0/1 knapsack, where every item is one of a kind. You use it once or not at all. To make that work in your code, you have to iterate through the capacity backwards. But then there's unbounded knapsack, where you have an infinite supply of each item. To allow for that, you iterate forwards. It's a tiny change in your loop, but it completely changes the problem you're solving. All right, let's look at a close cousin, the subset sum pattern. This one's a little different. Instead of maximizing value, it's asking a simple yes or no question. Can you find a group of numbers in your set that adds up to an exact target sum? And the metaphor for this is just perfect. Think about it like you're trying to cross a river by hopping on stepping stones. You start on the shore, which we'll call stone 0. Every number in your set represents a possible jump size. So if you have the number 5, you can jump from stone 0 to stone 5. From there, if you have a 3, you can jump to stone 8. The question is just, can you, through some combination of jumps, eventually land on the stone marked with your target number? Okay, let's switch gears now. We're going to move on to our next category of patterns. We're shifting from making choices about separate items to finding optimal properties inside sequences, like arrays or strings of text. And a real pillar of this category is the longest increasing subsequence, or LIS. Here, the goal is to look at a jumbled sequence of numbers and find the longest possible subsequence within it, where the numbers are in sorted, increasing order. And remember, they don't have to be next to each other in the original array, just in the correct relative order. Now, this slide shows this brilliant analogy for solving LIS in a really clever way. It's like a card game called patient sorting. Imagine each number is a card you're dealt. You take each card one by one and place it on a pile. The rule is simple. You have to place it on the leftmost pile where your card's value is greater than the card on top. If you can't find a pile like that, you have to start a new pile to its right. And here's the crazy part.
When you're done, the total number of piles you have is the length of the longest increasing subsequence. It's an amazing trick that gets you to the hyper-efficient O of n log n solution. Next up, let's talk about the longest common subsequence, or LCS. This one is absolutely fundamental for comparing two different things. Think about how GitHub shows you the difference between two versions of your code, or how scientists align strands of DNA. Under the hood, that's all powered by LCS. The absolute best way to think about this is with a 2D grid. You put one string along the top and the other down the side. Now, as you fill in the cells, whenever you find two characters that match, you get to build what I like to call a diagonal bridge from the cell just up and to the left. This bridge carries over the length of the subsequence and adds 1 to it. If the characters don't match, you just take the best value you've seen so far from either above you or to your left. Your goal is to find the longest path of these bridges to the bottom right corner. Okay, for our final category of patterns, let's look at problems that are structured a bit differently, often as grids or long chains of operations, where the goal is to find some kind of optimal path or grouping. So this slide highlights two really common examples. On one hand, you have grid P. This is all about finding the best path, maybe the shortest path, or the path with the maximum sum, or even just counting unique paths, from a start point to an end point, usually with rules like you can only move right or down. Then, on the other hand, you have a trickier one, matrix chain multiplication. The challenge here is fascinating. It's not about doing the math to multiply the matrices. It's about figuring out the most efficient order to do it in, where to put the parentheses, to minimize the total number of little calculations you have to do. Phew, okay. We have covered a ton of ground. So the big question is, how do we take all this knowledge and turn it into a concrete, practical playbook that you can use in your next coding interview?
Let's start with a little summary. Think of this table as your DP cheat sheet. It gives you the typical time and space complexities for these core patterns. Knowing these cold is a massive advantage. It lets you sanity check your approach on the fly. For instance, if you get a problem and you think, this feels like I'm picking items with weights and values, your brain should immediately go, that sounds like knapsack, so I should be aiming for a solution around O of n times capacity. And finally, here are a few pro tips to really make you stand out. Before you write a single line of code, always explain your logic out loud. Say, okay, my state will represent this, my transition will be this, and my base cases are this. Show them your thinking. And be proactive. Mention space optimizations like how you can often solve a 2D grid problem using only a 1D array. And of course, practice. Practice a few problems from each pattern until recognizing them becomes second nature. So, to wrap things up, you now have the toolkit. You have the patterns to break down these big, scary problems into smaller, manageable pieces. Which leads me to one last challenge for you. Think about a problem like partition equals subset sum, where you need to check if you can split a set of numbers into two groups with the exact same sum. Can you see how that's really just a knapsack problem in disguise? I'll leave you to think on that one. Thanks for tuning in.